мой звук ничего не отвечал. Смотрите, там перемещаем. Да. Ctrl-L, да?
Ctrl-L.
Ctrl-L, да?
Да.
Импульсор.
Говорит, завод.
Что-то не то. Что там завис?
Вот, сейчас. Загрузка идет.
Что это такое?
Я не знаю.
Смарт-тавы.
Okay, great. Who will present our speaker?
You.
All right. No. Better someone who
Ну, я думаю,
скажите что-нибудь.
так. Что?
Надо закрыть и открыть заново.
Это может быть скрывать.
KPZ. We have actually experts on KPZ here, but our former colleague Kudris was working a lot on KPZ systems. I don't know if he is online.
I guess not.
А нас в Zoom это видно?
Нет, это не видно, естественно. Должна быть зеленая рамочка вокруг этой штуки, тогда будет видно. Ну, escape, наверное.
Ну вот он
Escape.
не работает.
Может, ничего не работает? В Zoom нас видно? Можете кто-нибудь сказать? Владимир.
Так, вы меня спрашиваете?
Да. Вы потому что...
Я вас слышу, но ваш звук очень плохой. Он дребезжащий.
Презентацию видно?
Презентацию видно.
Пустой.
Okay,
dear colleagues, today we have speaker from Bogoliubov Institute for Theoretical Physics, Alexander Povolotsky, who is going talk about Kardar-Parisi-Zhang universality class and exactly solvable model.
Bogoliubov Institute is in Kiev.
No, it's not Bogoliubov. It's Joint Institute for Nuclear Research, Bogoliubov Laboratory of Theoretical Physics. But in fact, this laboratory is as large as an institute. So, okay. How can I? it doesn't work.
No.
Yeah,
You
it's,
can actually
Why?
point out.
I just
Yes, you can point out just where is mouse. But
not фокус есть. Мышка, да.
yeah, but
Я
you
понял.
cannot point.
Okay, so thank you very much for inviting me here and giving an opportunity to present a talk.
Вот. Блин.
Basically my talk will be about exactly solvable models and how they can be used to extract an information about very universal phenomena in nature. And I will start with two motivating examples and then outline my plan. So basically, I will start with things which are very well known to all of us, I guess. These are two statements from you see 16th century, which are, in my opinion, are main achievements of probability theory before the 19th century, let's say. They are called law of large numbers and the central limit theorem. So basically, and these examples will show you that there are very universal statements that do not depend on the details of what it started with. Basically, law of large numbers says as follows. Suppose you have a sequence of independent, identically distributed random variables, and you organize them into the sum, and then you so sum as far as all individual variables are random, sum is also random, but then you divide the sum by the number of these variables, and the law of large numbers says that under some very moderate restrictions on these variables, this random variable, the sum divided by the number of the variables, will behave at large number n as a non-random variable. Basically, it will tend to non-random number, which is simply an average of one of them. Law of large number is in particular responsible for existence of the thermodynamics. You have statistical physics system looks like a random system on macroscopic level, but when you look around on the microscopic size, microscopic scale, you don't see anything random. Then the second one is the central limit theorem, which says about how the deviations from the law of large numbers behave. What deviations you can actually observe with a finite probability. So you take your sum Sn, you extract the average of the sum n mu, and then you have to divide, you have to choose appropriate scale, such scale that the numbers of this on the scale, when the numbers at the scale being finite with a finite probability. So basically, the scale which is involved in the central limit theorem is square root of n. So you divide the deviation from the average by square root of n, and then the probability to observe something, some value of this variable is just its density is just a well-known Gaussian function. So it's a standard normal random variable. The main point is as follows. When you appropriately choose the scale, you see law of large numbers and central limit theorem, and the distribution within the central limit theorem almost doesn't depend on what was on the microscopic scale, if you rescale it in a correct way. Okay? And this is why the Gauss distribution is everywhere around us. So basically, there is less known and more modern achievement, which is more modern to probabilists, is so-called functional central limit theorem, which says the following. If you now consider the sum as you insert the number of the sum, some continuous parameter t, which will vary, for example, from 0 to 1, and then you will send this number n to infinity, then you will now get already not a single random variable, but you have a random function. You have a random function of the parameter t. And this is a random function. This is so-called random process. This random process, the limiting random process, is called Brownian motion or Wiener process. And how you define it, you have to, for example, calculate all the correlation functions of this process or multi-point distributions. For example, probability that at time t1 it's less than a1, time t2 less than a2, and time tk less than ak. If you have these multi-point distributions for all numbers of points, you define the measure actually on the Wiener process. Well, this is sort of universal things. So again, you started with some random variables which constitute the sum S, and then well, these variables could be continuous or could be discrete. They could have finite or infinite support and so on. But finally, you get the universal random process where the multi-point distribution are just combined from these Gaussian distributions. Well, so basically, these are sort of universal statements which I want to do for more complicated cases. And this is my outline. So basically, the answer which I will, the question which I will answer is there any universal statements like that beyond the realm of the independent random variables? So I will tell about, for example, growth processes where advances of the growth are not independent. But nevertheless, we can state, we can make some very, very universal statements about this, and this is my outline. First, I will tell you about, well, I has told already about universal scaling for independent random variables, and now I will tell you about real-life systems where the universality was first observed and then later was actually explained in a very detailed fashion. Basically, the main systems where it appears is in random growth of interfaces, but then you need to get the some analytic description of it. You basically, it's not that simple as this central limit theorem and large numbers. You need much more involved methods. And for that, the idea is as follows. You have to find some exactly solvable model. And due to universality, in some certain scaling limit, this exactly solvable model will give you the correct answer in a certain scaling limit. So basically, I will first give an example of very well-known exactly solvable model, and then tell about the work which I was involved, about some other more general models and the results for them. So the answer which the question which I answer is the universality beyond independent identical distributed random variables, and the system is as follows. You can think about basically the basic system which I tell about is interface random growth of interfaces. You can think of napkin, for example, put with a corner and coffee, and then by capillary forces the liquid goes up, and the boundary here is random. So it has some macroscopic shape, and some random deviations about it. And what I want to do, I want to characterize the statistics of this random object. Basically, the universality, the fact of universality is confirmed by observation of the same behavior in very, very different systems. And there are examples like combustion, wetting, solidification fronts, turbulence and pneumatic liquid crystals, borders of bacterial colonies, and so on. And there are different languages which you can say about the systems. For example, the same things can be observed in traffic flows. Also, it can be said about polymers in random media. And recently, it was the KPZ universality was also observed in polyurethane condensates. So basically,
yes, can
yes.
you comment on the dimensionality of the system? So in polyurethane condensates, it was in one-dimensional, and now perhaps also in two-dimensional systems. What kind of
Well,
systems?
we believe that KPZ universality is for all dimensions, but exact results exist only in one dimension. So basically, I will tell about one-dimensional systems, but the KPZ equation was written for the for any dimension and analyzed in any dimension, but still no much achievements there. Well. Okay, so basically, what is the random universality and random growth of interfaces? This story started in 80s of the last century, and people observed. Then, when you look at the interfaces, like I just mentioned, there are basically two stages of the development of the interface. First, the interface starts to. There is a so-called Raufening transition. You start, for example, from some smooth interface, and that is there are random fluctuations, and they start to grow. On the early stage, they grow as a power law of time, and then if you consider a finite system, at after some time, there is a critical time in the system which is related to system size as a power law. After that, the width saturates, and the width of the interface will be related to system size by another power law. Okay, basically, so if you consider the width of the interface, this is the variance of the deviation of height from its spatial average. Then there are, you see, two stages. And there is a set of critical exponents. The zeta is here, is Raufening exponent, alpha is here, is fluctuation exponent, and the time is defined by the dynamical exponent. And then if you also assume such a scaling ansatz that these two regimes should be sewed together. Then basically you observe that out of these three exponents, only two are independent and they have a relation. Okay. Now people started to measure this, to find this, to look for this, for analytic description, and they on one hand they created the models for computer simulations, and on the other hand, they tried to write some continuous equation which would be universal. So the simplest example is so-called random deposition. You just drop the bricks on the plane on fixed spatial positions, and they just put where they just come at the horizontal position. At any horizontal position at random. Well, in this case, it's quite clear that when they don't know about the neighboring bricks, at every spatial positions, they are just independent. So basically, if you remember the picture I explained you in the previous slide, there is no late stage because it's never saturates. They all grow independent. They don't know about each other. They never get correlated. That means that basically the fluctuation exponents just comes from the central limit theorem for every special point independently. But there is no correlation, so the critical exponents z and z can be formally set just to infinity. And the continuum limit, if you will start to like look at this system at the large scale, will be just described by the fluctuations around the average will be just described by Brownian motions of the height at every point, and they are independent of every spatial point. Well, of course, this is not a natural situation, and the next attempt was to include some condition which keep the interface relatively smooth. And then what you have to add to this equation, you have some smoothing mechanism, which is a Laplacian here. Well, this this equation is called Edward-Wilkinson equation. It's actually linear equation, though stochastic, because this eta here is a white noise. It's a Gaussian random variable, which is delta correlated, so independent at different points and is a delta function at the same point. So basically, here also you have this Langevin type equation, but then it can be solved, and the critical exponents can be found. They can be compared to experiments, but already here you can see one disadvantage of this equation. It's invariant with respect to interchanged up and down. So basically, which is not natural for growth process which we observe in nature. This situation is realized in the, for example, when you have phase boundary in the situation of thermodynamical equilibrium. For example, here consider the Ising model, and in Ising model, the minimal energy. So you have system of spins, interacting spins. And suppose this is ferromagnetic model, so minimal energy is for the system where all arrows are the same, have the same direction. But then if you have infinite system, you can, for example, start with this phase separation boundary, and then you assume some Glauber dynamics on it, as usually people do in numerical simulation, where spin can be allowed to flip. And the probability of this flip is kind of ratio of two Boltzmann weights of two configurations, which finally leads you to the Gibbs measure on these configurations. And at t equal to 0, basically only flips which do not lead to the energy change are allowed. So basically these flips are where only the border can flip here, on the where it has corners, like here. This is if you let this boundary to evolve, it finally gives you some random shape, and this random shape will be just described by these critical exponents. But as I said, this symmetry with respect to direction, change of direction, is doesn't make it appropriate for non-equilibrium processes. And then the third model, which seems to be more natural, is ballistic deposition, where you also drop the bricks on the plane, but then they stick where it meets the first neighbor. You see? And then if you again let this system to evolve for some time, you observe some random boundary, and this boundary, which will be much more complicated, and you can run this system on computer simulation, you will see that it can be behaves exactly as I just told you, and they will be described by this set of critical exponents. So how to incorporate this interaction with nearest neighbors to this Langevin type equation. Of course, you introduce some function of, well, you want it to be local, so it should be at least function of gradients or derivatives, not of h itself. And then you start, as usually physicists do, expand this force, this interaction in powers of gradient. It turns out that the only relevant term is the second power, which this is term which changes this scaling behavior. As far as you added this term, you go from this exponent to this exponents. This is all exponents for one dimension. And the next terms are not relevant here. So basically, what we call the system of KPZ class is as follows. You take, for example, interface, and then you rescale it. Let me go here. You rescale. You have to divide, for example, if you consider the situation of large time, you have to divide your fluctuations of interface height by t to the 1/3, and then so it will give you some you have two analogs of laws of large numbers and central limit theorem. So you have a microscopic shape, and so your interface height divided by time at large time is just the non-random deterministic function of rescale position. So it's just this curve, smooth curve. And then if you extract this smooth curve from the height, you look at the fluctuations, you will something at the scale t to the 1/3, and then here you will have something random. And this random is just your analog of the central limit of Gaussian random variable in the central limit theorem. And then you ask about the distribution of this quantity. But also you want to look at different points here. At what scale you have to have distance between these points for these fluctuations to be non-trivially correlated. So basically, here you will have another critical exponent beta, which is simply 1 over z. Z was dynamical exponent, so beta 2/3. And then, so here you define your spatial positions, high few, as shifted by these quantities of order of t to the 2/3. And then you ask these quantities how they are correlated. So you ask about multi-point distributions of this quantity. We define you the whole random process, all this curve. Okay. Well.
What's the meaning of the square of the gradient?
I'm sorry.
The physical meaning of the gradient.
Physical meaning of
gradient square. The lambda over 2 partial x square. Was the physical meaning of
this one. Well, this, if you, in terms of interface, this is the term which is responsible for backward growth. So basically, if you have a shape, Laplacian says that you cannot, it's smoothing it. Okay, and this, yes, and this one, it leads to backward, how it's not backward, lateral growth. Okay, so as far as you have slope, it's growth.
Lambda is positive.
Lambda can be positive, can be negative, no difference, basically. Well, and now I will show you examples of these limiting distributions here. There are two very well-known examples, FGOA and FGUE. So this is abbreviation for Gaussian orthogonal ensemble and Gaussian unitary ensemble. And their analogs, well, their generalizations, area 1 and area 2 process. This is a random process which are defined as a set of correlation functions, set of multi-point distributions, where one point distribution is these distributions for random variables. Let me tell you a couple of words about this. So they come actually from the theory of random matrices. This is so-called Tracy-Widom distributions. Suppose you have a matrix where n by n random matrix, which is Hermitian, and so the matrix elements, the coefficients of this matrix above and at the main diagonal are normal random variables, and diagonal and off diagonal, the variance of them are twice are different by the factor 2. And so Gaussian orthogonal ensemble, it includes the real symmetric matrices, and Gaussian unitary ensemble, it includes just the Hermitian matrices. Okay, up to that, they all only composed from independent random variables, normal random variables. And then there are, you can start, as far as matrices are random, you can diagonalize them, the eigenvalues will be random as well. And then there are also laws of large numbers and central limit theorem for this, for the eigenvalues. And I will only mention the ones for the largest eigenvalues, so the maximal eigenvalues. So with probability 1, if you take lambda and divide by square root of size of the matrix and sends n to infinity, then this ratio will converge to 2. It's just, basically I didn't write here, but there is a density of eigenvalues, and this so-called semicircular Wigner law. There is just a semicircle, the density. And the edge of this semicircle is just square root of n times 2. So basically, if you divide, then it will be 2. But then you look at the deviations from lambda divided by square root of n minus 2. And the deviation turns out to be of order n to minus 3/2. And then for the orthogonal ensemble, you will get the random variable. This random variable will converge to the random variable, which is called, described by the distribution of GOE, and for real symmetric and for Hermitian matrices FGE. This is what.
Sorry,
yes.
Minus 2/3. Yes?
I'm sorry?
And to the power. I was confused. You mentioned some power minus 3/2, but I see power 2/3.
But it's not divided, it's multiplied, right? So for this to be fine, this should be 1 n minus.
Be inverted.
I think basically, yes. I think I did a mistake. Here it's 1/6. I'm sorry. So, and these are, these distributions are very well known nowadays, though they cannot be written in simple analytic form. They can be written in terms of the Fredholm determinant, such a Fredholm determinant of integral operator with a given kernel, which can be defined by this infinite series. Though this is quite a complicated representation, we know everything about these distributions, mean, average, some other moments, their asymptotics, and so on. Also, these distributions can be related to special solutions of so-called Pinlevy equation, and this is how their asymptotics are studied. And also there are, I mentioned also the generalization of them for the random processes, ARI1 and ARI2, for which these functions are one single point distributions. So basically, this is what is written here. I will not show you how they are represented, but also they are given by these multi-point distributions are given in terms of Fredholm determinants with some more complicated kernels. Well, let me now show where the people measure this. They basically, I mentioned these experiments, and they are now there are now very precise experiments where surprisingly, they measure these very complicated functions. This first experiment is a paper combustion. So there is an you put the paper into the medium with a few oxygen for it to burn slowly. And then there is an ignition here, and then the combustion front start to propagate. And it's random. You make this experiment very many times. And then you make a statistics. And this is what they get. Basically, if you properly shift it and rescale by 10 to 1/3, you get this Tracy-Widom distribution from GOE. So this GOE, it's due to the fact that you started with a flat initial conditions. There are like 3 types of initial conditions which are exactly solvable in a sense, for which you can get the closed formulas. And flat is one of them, and it leads to GOE distribution. And the other experiment is very nice experiment with the turbulence in the liquid crystals. There are pneumatic liquid crystals, and there are 2 phases, which are one phase they are different in concentration of some topological defects. I'm not an expert in this, but what they say, it's put in the electric field between the planes of transparent capacitor. And then they make, they are in a metastable state, and they make by the laser instability nuclear, and they start to grow. And then you study the statistics of this random boundary, and again, for the circular geometry, you get Tracy-Widom GOE distribution, and for the flat initial conditions, you get Tracy-Widom GOE distribution. Well, now let me go to my point, how these results can be obtained. So the way, as I said, find something exactly solvable. Now I will show you some exactly solvable models. They may seem to you very simplified and unnatural, but the main point here is the universality. So as far as you get the exact results from them, these exact results, of course, has nothing to do with real systems. But as far as you take a scaling limit, the scaling limit gives you exact functions.
And this KPZ equation itself is not what you mean by exactly solvable model.
It is. I will mention about this in a few slides. So basically, this is asymmetric simple exclusion process, which is related to so-called solid-on-solid interface. It's defined as a system of particles in the lattice, and particle configuration is just a string. If you have, for example, n sides, it's strings of n numbers, which every of these numbers is 1 or 0. Corresponding to particle or empty side, and then it evolves in time. At any moment of time, it jumps left or right with rates L or R, which basically means that it jumps with probability for the time dt with probability L dt and correspondingly R dt. Okay, and then well, if you consider this, one of the versions of this model is and now you can associate these configurations, which a broken line drawn on the plane. For every particles, you can have a line which is 45 degree on the 45 degree square lattice. Well, this line goes down, and for empty one, it goes up, and so on. And you just associate these configurations to this line. And then as far as particle jumps here, you can see it can flip here. And it jumps here, it can flip here. This is exactly what was when I shown you the phase boundary in the Ising model. with only difference that now you can make R and R different, because there they were equal. And this difference makes the deal. You get KPZ system instead of Edwards-Wilkinson. Well, basically, if you want, now there are questions of boundary conditions. You may consider, for example, infinite system, or you may consider the ring. And if you make a ring out of this system, you have to draw this interface on the cylinder with so-called helicoidal boundary condition. You should cut it along the vertical line and shift. Well, basically, so when L is not equal to R, this is KPZ class, and where L is equal to R, this is Edwards-Wilkinson class. Okay. Now, why this system is good? Because it's integrable model. I will not tell you the details of the integrability. I will show only this slide to give an idea where the integrability comes from. Suppose let us consider a Hilbert space, which is a tensor product of n two-dimensional spaces. And then I associate the basis vectors of this space with just the tensor products of this is basically this space is a Hilbert space for the quantum spin chain of n1/2 spins. And you have vector E0 corresponding to spin down and E1 corresponding to spin up. Okay? And then every configuration of particle is associated by just the configuration of up and down spins. Up spin for particle and down spin for the empty side. And then you work with the probability distribution. So for probability of distribution of configuration at time t, you associated this probability vector. You just probability of configurations just sum up with these vectors corresponding to configurations. And then if you want to write the equation for the evolution equation for the probability, is called physicists call it master equation, mathematicians Kolmogorov equation. It will look exactly as XXZ type, the equation for a Schrödinger equation in imaginary time for the XXZ type quantum spin chain. And this can be solved by the methods also applicable to XXZ spin chain, which is called Bethe ansatz, and all the toolbox of the theory of stochastic of the theory of integrable system is applicable here. This is this Hamiltonian is not exactly. It becomes Hermitian when you make L equal to R, and when you make R equal to R is exactly XXX Heisenberg Hamiltonian. But when you break this L and R symmetry, then it's yes. Now I will tell a couple of words about a discrete version of this model, and and about its solution. Not to explain you the solution, but just to explain you some other languages which these problems can be told on. Can be for which which can be used to tell about these problems. So now I consider the total asymmetric exclusion process. Total, it means that they jump only to the right, and in discrete time. So there's just discrete time, and every step, every particle decides to jump or not to jump forward, so that it jumps forward when there is a empty side here with probability p and stays with probability 1 minus p, and jump to already occupied side is forbidden, exactly as it was before in continuous time picture. Well, This is called parallel update. So basically, the question which we ask is as follows, the simplest question. What is the probability that, for example, you start with the initial configuration on an infinite lattice where all particles with negative numbers are occupied at the initial time moment of time, and all of them are empty. All sides are empty to the right of the right half. Well, and you ask, what is the probability for a particle number n to make m steps for time t? Okay, so basically, exactly with the same mapping which I used before, this picture can be associated to the line. And when they start to jump, this line will evolve, and then you want to look at it in a large scale. So this is the initial condition. And then this is how, if you introduce, for example, the integrated current, the number of particles that cross the bond x minus 1x by the time t, the advance of the height will be just twice the current. Okay? And then you can ask about what I said, what is the probability that particle jumps m steps, and this is related to the probability distribution of this integrated current, and this is related to the probability distribution of advance of your height function. Okay? Well, and these are just answers which which were obtained. Well, first of them in 1981. This is law of large numbers, which says that if you divide this by time and scale the spatial positions by time, that it goes to deterministic function, which is basically a parabola, actually. Well, for continuous time, it's a parabola, and for discrete time, it's a bit more. It's non-universal, but the universal fact that it's non-random. And then CLT, so circle limit theorem, you extract the average, you define by t to the 1/3 with some model dependent constant dependent on p, and it converges to a random variable, which is FGUE from this random matrix theory. And then functional CLT, you also allow the spatial positions to vary on the scale 2 to the 2/3, and then you again extract the average value, normalize it by t to the 1/3, send t to infinity, and you get every two process which I mentioned before. Well, these are answers. Now I tell a couple of words how to come to these answers. As I said, not to explain you the solution, but just to present you several other problems where this KPZ universality appears. First problem is as follows. You can represent the evolution of the step as a set of waiting times, the number of steps particle waits every particle number of steps, particle number I waits before making step J. Okay, and you can organize this to such matrix. So this number of steps, so when particle starts to wait, when it can jump, so it doesn't jump with probability q. So if it waits k steps, the probability q to the k. And then finally it jumps, so probability p to jump. Every of these numbers is independent, geometrically distributed like this, random variable. So you have a random matrix. And then this quantity which I mentioned, the waiting time, the time which particle number n needs to make m steps. It turns out just you have to take this matrix and you have to construct all possible directed paths which go down and right from here to here, from 1, 1 to nn. And then it turns out that this time which you need to reach to make m steps, the nth particle, is just the maximal sum over this path. So you have to draw all the direct paths and choose the one where the sum is maximum. Okay. Then you can relate the distribution of your time, which is called last passage time, and this problem is called last passage percolation problem. This is another interpretation of KPZ like physics, last passage percolation problem. It have different forms, but this is probably the simplest one. Then the next, another way to look at this is as follows. Consider a random polymer, a polymer in a random media. These paths will be polymers. And the energy of these polymers will be minus the sum over these numbers, matrix coefficients along the path. Okay? And then, well, partition functions will be just this, the sum over all possible paths. Free energy is logarithm of partition function, but if you send t to 0, your free energy becomes just energy, right? And minimal, it becomes a minimal energy, energy of the paths which minimizes it. Okay, and it means that your time, which nth particle needs to make n steps, it's nothing but the minimal energy of the random polymer. Okay, so basically another phase of this problem is a polymer minimizing the energy of polymer in a random medium. Then another problem. It turns out that you can represent map this matrix of integers to so-called generalized permutation. Generalized permutation is a two-line array in which in first line the numbers weakly increase, and if they do not increase, the second time they should weakly increase. So basically, usual permutation, you have numbers from 1 to n here, and here they are permuted. And generalized permutation, they can repeat. Well, this is the example. And if you can now record this matrix as a generalized permutation. You just take first one, the pair of indices, for example, 1, 1 is a vertical and horizontal index. You pair as many times as this number is. So 1, 1, 2 times, then 1, 2, 3 times, then 1, 3, 1 time, and so on. So basically, there is a one-to-one correspondence between random matrices and generalized permutations. And then this maximal path, which I mentioned, is nothing but the largest non-decreasing subsequence of this second line. Okay, so you have to now look at the distribution of these largest non-decreasing subsequences. And this problem is a so-called boarding problem. Suppose people go to the plane, and every of them in a random order, and every of them have to put their luggage on the shelf, and it spends 1 minute. And as far as the order is random, the time which boarding takes is also random, and it's just this waiting time which is goes here. Well, and finally, the last correspondence. This generalized permutations. I forgot to say that first line and second line are taken from the alphabets 1 to n and 1 to n correspondingly. So basically, one more correspondence says that this generalized permutation can be mapped to a pair of Young tableaus, semi-standard Young tableaus. It's a Young diagram filled with numbers which weakly increase in horizontal order and strictly increase in vertical order. And this time TMN is just the length of the first line. So you have to now take all the Young tableaus of the same shape, and then look for the distribution of the length of the first line. It will be this problem comes from the representation theory. I will not tell about this, but also you can study how the representations of, say, symmetric group or other groups look like when the group becomes very large. And finally, I return to the KPZ universality. Basically, why the Kardar-Parisi-Zhang equation is a model of Kardar-Parisi-Zhang universality class. Basically, on the same reason, if you rescale, if you take H, extract some average density, which is infinite here, there is some regularization, divide by t to the 1/3, you will again obtain the same GE and GOE distributions when you start from so-called wedge initial conditions, though infinitely narrow wedge, and flat initial conditions. And how you people get this, and why is it integrable? Basically, this equation understood as in a naive, just simply like it's written, is meaningless because this H is something like a Brownian motion. It's a function which is continuous but nowhere differentiable. Then you can understand the derivatives in a weak sense. It means that in the sense of generalized functions, but nevertheless you cannot square the generalized function. So this how to understand this is not an easy task. And basically, in this how to understand the equations like this was explained only in 2010, for which Martin Heyer obtained the Fields Medal. But before that, people went another way. Let's look not at H, but at e to this combination, the exponentiated H. Then the equation for the Z will be already linear. Okay, it's just a stochastic heat equation or Schrödinger equation in imaginary time with a random. This V is just the noise. So with a random potential time dependent. Well, then as far as you have this Schrödinger equation, you can represent the solution formally at least as a Feynman integral. Okay, and this Feynman integral is just an integral over the trajectories x of t from y to x, and this is just a partition function of polymer and random media with random potential v. Okay, then what you are interested in, you have to. This is a random quantity because this v is random. So you have to know the statistics of free energy. And these statistics of free energy can be obtained via the so-called methods of replic, which, well, when you write the equations for replics, it actually can be reinterpreted in terms of integrable Lieb-Linear bosons with attracting delta interaction. And this is exactly solvable model. So you solve this model, and then you return to the distribution of free energy, and free energy is just lambda times h.
How much time will we need?
I'm sorry. Yes, I will probably don't have time for my own results, so I just show you a few pictures. And sorry. So basically, what I want to now I want to extend this picture. First of all, I want to ask how universal is the KPZ universality. So I want to find other models with richer dynamics and ask when they fall into KPZ class and when the KPZ is broken. Okay, and I just formulate you two models and say their features and say maybe very briefly what results we obtained for them. Okay, so first of all, we search for integrable model, and we look and we ask which is as much as possible general model with as much as possible general dynamics. And the model which we start with is the following. You have particles which now can be at the same side, any number, and they jump in the same direction with probabilities which depends on the number of jumping particles and on the number of particles that were in the side. Okay, so you have two particles jumping out of this side with three particles with probability 5 to 3. And they updated in parallel, and the time is discrete. Well, and we asked when this model is solvable by the beta ansatz. I skip the details, which I prepared for you. And basically, it turns out that we have three parametric family. These probabilities, they depend on three parameters, mu, and q. And it's quite rich family, which also include, for example, this TASEP, which I just shown you. Basically, this multi-particle model can be converted to particles where only one particle inside is allowed simply by replacing this column by this plus one empty side. And then, then there are a lot of particular cases which were studied before and which were studied after this model was invented. Let me just mention that when the parameter q is equal to 1, this is just a binomial distribution. This jumping probabilities means that you choose at random n particles out of n particles. It means that every particle just try to jump independently. It's just a non-interacting particles. And then as far as you switch on q and other parameters, you can interactions of different kinds. Well, so basically now I go to two particular cases. I just formulate the models and probably finish. One of them is a symmetric avalanche process. It's a particular case of that model, though it was proposed much earlier. And we returned to it quite recently because new methods became available. So it's defined as follows. You have particles, they jump with rates r and r, right and left, and now they can come to occupy side, but as far as they come to occupy side, the so-called avalanche appears. The avalanche can pick up the particle and go bring it to the next side. And there is a probability to that it picks up the particle mu n and 1 minus mu n, it leaves the particle at the side. So there is such avalanche which goes through the system, and finally, again, all particles remain at most one at the side, the avalanche stops. What's special, and this model can be, of course, also mapped to an interface. This is a general mapping for multi-particle systems, but in this case can be only one column larger than one. So you this line makes a jump, which vertical jump of the same height as the number of particles in a side. And basically, what's special about this model in the thermodynamic limit? There is a phase transition. There is a critical density. Below the critical density, the average the average speed of particles or the average avalanche size is finite, and the buffer is infinite, and the infinite system. And then we were interested how the current and fluctuations of the particle flow are organized, and I will skip the details. And another system which I want to mention is the so-called TASEP, totally asymmetric simple exclusion process with generalized update. It's also a particular case of the model I just shown you with the parameter q is equal to 0. And it's organized as follows. So almost as discrete time TASEP, which I shown you before, but here you, when you update the cluster, first particle of the cluster jumps with probability p, and the second with probability mu. And then we can vary. For example, when you mu is equal to 0, it's just the discrete time TASEP I shown you. When mu is equal to p, it's so-called TASEP with backward sequential update. You just update all particles one by one from right to left. And this is generalized update, and what we were interested in. Again, what we obtained at general p and mu, these systems is simply falls to KPZ class. All the large-scale fluctuations are KPZ distributed. And but then there is an interesting limit when you send mu to 1. This is so-called deterministic aggregation limit. Particles start to collect to large clusters, and then there is certain, well, this cluster will grow, and the scale changes. And you can observe actually other scaling limits other than KPZ, which gives you other limiting distributions and limiting processes. This is just pictures how they look like for mu equal to 0. It is just a parallel update TASEP. And this is for mu close to 1. It's almost deterministically moves forward with a rare empty size here. Well, and then we ask how these deviations about the average are distributed. And they, of course, in this case, they are distributed in the KPZ scale. And when they are almost all in one cluster, it's just random walk, they are distributed diffusively, well, in the diffusive scale. And then we ask about the crossover, which I also don't have time to tell about. Well, these are answers. This basically the plots of the current versus density. And you see that when mu is equal to 0, it's symmetric because there is a particle Hall symmetry. And when mu approach 1, it approaches straight line. And the density of particles then also it smoothly decays at low mu, and then it approaches just a step at mu goes to 1. Well, and there are fluctuations, and there are different processes which I skip. And here there is a scheme of limiting processes. Finally, you have a limit when all particles just stick together and move as a single particle, and fluctuation are purely Gaussian, but there are some transition scaling limits. So this is area 1 and area 2. These are just KPZ, and these are transition scaling limits. Well, these are unsolved problems. First of all, these results which we obtained, they obtained as the distributions are represented as some complicated and Fredholm determinants. And finding the asymptotics, for example, of the study of these Fredholm determinants is a special activity. It requires lots of many complicated techniques. It's an open problem. Then nobody solved the system, these distributions, non-stationary distributions of generalized TASEP on the ring, and also the G-TASEP on a segment. We know now how it has a non-trivial phase diagram. There are so-called boundary induced phase transitions. If you have a chain, finite chain attached to reservoirs of particles. But we know how the phase diagram look like, but no exact solutions exist at the moment. And these are references to papers which I mentioned. Well, thank you.
Questions?
I have a question, actually. In all problems that you said, you always consider one-dimensional or mapping to one-dimensional problems.
That's true.
But what about two-dimensional and for polyrhythms, for example, what's the difference
Well,
between dimensions?
I have partially answered this question already in the beginning. There is in 2 dimensions, there are models, of course. You can consider exclusion process in 2 dimensions, but nobody can exactly solve 2 plus 1 dimensional models. And the KPZ equation is also written formally in 2 dimensions, and even people write some results on it, but at the moment these are very, very low-level results, like stationary state or something like that. No exactly solvable science in 2 plus 1 dimension exists. You see, that's the problem.
But you try to first of all exactly solve to use exactly solve
That's true.
model.
No, there is a lot of
apply to some physical realization of this model.
right. There is a lot of simulations. There are renormalization group techniques, the field theory techniques applied to this model. People calculate critical exponents. But the problem is with this KPZ physics, for example, it doesn't have the upper critical dimension. So when you make a renormalization physics, a renormalization group, you should use some very elaborate functional renormalization groups, and you cannot control the accuracy and so on. This is very, very open question. So I welcome everybody to work on it. But at the moment, beyond 1 dimension, nothing, even critical exponent are not known exactly.
But I comment on what happens with polarities. So experimentally, they measure coherence by interferometry, optical interferometry in arrays of polarity condensates, and they measure how the first order coherence depends on time and on the coordinate. There is a published paper from Jacqueline Bloch group where they did it in a 1-dimensional chain of condensates, and they obtained this KPZ scaling. And there is also another paper which is about peer, where they did the same different group in a 2-dimensional array. Now, interpretation is based on brute force numerical simulations with Gross-Pitaevsky equations coupled to some diffusion equations for reservoir. And of course, as in all published papers in the world, theory exactly reproduces experiment, which tells you nothing of the origins of this scaling. So I think some analysis here would be really helpful to clarify the physics that is behind this observed scaling. Well, it is observed, and what? That is my question. What does it mean? That it is observed also in 2 dimensions. Actually, it is observed in a certain range of parameters, of course, not always, certain range of pumping, but so far I have no any clear understanding on what qualitatively is going on in this experimental system.
But how do they distinguish the KPZ from KT transition?
By scaling, how this coherence scales with time and with space.
It's well known that in 2D, the KP transition, the smooth reader or the PMC in the polariton will obey the law of KT transition.
Somehow it is distinguished in the paper. I don't remember.
But that's how you can have long-range order under the framework of KP.
I need to check on this discussion.
Well, so in your presentation, you talked about so many different models, and they all fall into the same result. So what's the common thing? How can if you see a new model, how can you tell if it's likely to fit also in the same result class?
You mean without measuring and calculation?
Yeah,
just
just like how do you take an educated guess whether the model will fit?
If it comes to interfaces, these are all interfaces which have local interactions and uncorrelated random force. So, or shortly correlated random force. Basically, this is what you have. As far as you start to have, for example, quench disorder, like you have some defects in medium and so on, of course, everything changes. You have to have kind of thermal fluctuations, which gives you uncorrelated random force, and local interactions within the interface.
Also, we have a question about the gradient term in the KPZ function. So will this term increase the long-range order or I mean increase the correlation in between? Correlation function.
Say it again, please. Sorry.
The gradient term in the
Gradient term. It changes the large scale behavior completely.
Will this term increase the
Yes.
correlation?
Yes. It not only increase correlations, it also decrease fluctuations. Because without this, no, increase fluctuations. Because fluctuations of Edwards-Wilkinson there is alpha is equal to 1/4.
Yes.
It's much less, yes, and this is 1/3.
I see. So this means that they will decrease the correlation.
So
If lambda is very large.
let's see. So the correlation scale will be grow with time. The fluctuation scale will grow with time as t to the 1/4 in Edwards-Wilkinson, as t to the 1/3 in KPZ, right? So KPZ fluctuations are bigger.
Yes.
And then the correlations is 1/2 in Edwards-Wilkinson, t to the 1/2, the correlation length, and t to the 2/3 in KPZ. So it's also make it more correlated. The correlation length is greater.
Fluctuation is higher, but also the correlation is higher.
Higher, yes, that's true. That's true.
It's interesting.
So the ceremony, we have a traditional gift.
Oh, thank you very much. That's very.
Who will be the next speaker?
Speaker Oleg Sakovich. Actually. Все.
Julie. Hello. Nice to see you. So, Julie, and we could discuss